And we have just enough time for me to tell you about the binomial distribution. When do we use it? We use it for binary events. So has does not have cancer. I don't know, what other examples have we had? Heads or tails. If we're talking about a dice roll, it couldn't just be the value of the dice. It would have to be, say, is it odd or even? There are two outcomes. Anything with two outcomes and only two outcomes. Whether or not someone has private health insurance. They either do or they do not. And if you're wondering if a certain question is about the binary or the binomial distribution, you can ask yourself these 4 questions. So first of all, we're going to phrase things in terms of trials. Now, it's a little bit strange language, but in the example of the dice roll, each roll of the die is a trial. In the example of cancer or not cancer, each individual who we observe is a trial. So a trial is something where we don't know what the answer is going to be, we make our observation, and then we know the answer. That's a trial. So the first requirement is that those trials are independent. The second one is that the number of trials is fixed in advance. So, or at least it's not dependent on the outcome of previous trials. So it's not like, okay, I'm going to keep on rolling the die until I get 10 even rolls. That's not binomial distribution. Binomial distribution is I'm going to roll the dice 10 times, or I'm going to go observe 100 people. It's not going to be I'm going to go collect individuals for my study until we have 100 people with cancer. That violates the number 2, that the number of trials is fixed, and your distribution would not be given by the binomial distribution. So the third one, that each trial can be classified as a success or a failure, that's just saying that it's a binary variable. This success or failure is the language of the binomial distribution. And the reason that we do that, even though that language of success and failure doesn't exactly make sense in a lot of cases, it's just a way of sort of standardizing the language so that when you go to do a calculation, to use a formula, you know how to calculate the probability. As long as you decide what the success is and what the failure is, then you can calculate your probability, say, of a certain number of successes. It's not always, you wouldn't always think of what we're going to call a success as an actual success. So in the example of cancer, we would probably call having cancer a success, just because we are going to calculate probabilities of a certain number of successes in the trial. And if you want the probability of a certain number of individuals having cancer, you're going to treat that as the success. You can always do it the other way. It's arbitrary. It's just a matter of what you want to calculate. Is there a question? All right. And finally, that this probability of success, or the relative probability of these two events, is the same for every trial. So, so it's not that it increases over time or changes in any way. It's the same for every trial. Is X sigma? No, I assume you're talking about this and this. No, X is the number of successes. It is. We will get to the normal approximation to the binomial distribution, and I'll show you how they're related. But they're not the same thing.
Good question to trial. When you're saying that, obviously when we're doing a trial, we go through whatever that event is.
Yeah.
And you don't know what it is, so we make an observation, and based on observation, that's the best. We say that's our best guess of uncertainty.
So your question was, is the observation that we have our best guess of the uncertainty? That's a tricky question. I think maybe what you're thinking of is if we observe, say, 100 trials and we observe 50 successes, then our best guess at the probability of a success is 50%, even though that's just a guess from a sample, and that's true. There will be uncertainty around that guess of a success probability of 0.5, and that will have to do with the standard deviation or the spread of this binomial distribution. Here are some examples of binomial distributions. So this red one is an example with n, the number of trials, equal to 20, with a probability of success each time of 5. So the most likely outcome is 10 successes out of 20. And you see this declining probability. So remember, this is a whole probability distribution. This is telling you if you go and do this thing, this event, 20 times, your probability of having 10 successes is this, about 0.17. Your probability of having 11 successes is a bit less, 12 successes is a bit less. So it's giving you all of these probabilities. Of course, when you go ahead and do that trial, you're going to get some particular number. Maybe you get 10, maybe you get 12. But this is telling you in advance what your probability of getting any possible value is. And as you get up to 20, your probability is pretty small, and as you get greater than 20, it's 0. So your probability of 21 successes is 0, or of some negative number of successes is 0. So it's a discrete distribution, unlike the normal distribution where there's any values possible between plus and minus infinity. Here there's only a certain set of values that are possible between 0 and 20. As you increase the number of trials, so the green one up to n equals 100 with a probability of 0.5, just shifts and broadens the whole distribution. With a n equals 100 and a probability of 0.3, it shifts it, but you'll notice it has about the same spread, or it has exactly the same spread as the previous case with probability of 0.5. And we'll get to that under the this large sample approximation. By the way, you'll notice I put a big equation on here without saying anything about it. This is the binomial distribution. You will get some practice in using it just with a spreadsheet. It looks complicated, but it's just algebra. As long as you know what n is the number of trials, x is the number of successes, and p the probability of success in each trial, then you can calculate the probability of getting a certain number of successes. So in that case, with n equal to 20 and probability of 0.5, you would plug in 20, p is 0.5, and if you wanted to know that probability of 10 successes, you would put x equal to 10. You would calculate this, you'd use the factorial here, and you get the probability of having 10 successes out of 20. And this isn't so bad to do once you have a spreadsheet. It is problematic if you start getting into really large n. If you try to take 1,000 factorial, you're going to have a problem in Excel. That's why we get to the large sample probability. Here's some examples. I'm getting a little short on time, so I think I'll let you work through these on your own, and in the lab downstairs you'll be getting some more practice. But this is a good example of a binomial distribution type of question. So if you have the prevalence of diabetes in an early population is 10%, and you randomly select 4 individuals, assuming that they're independently selected, not from a family, right? Because they have to be independent events. What's the probability that exactly 3 of them are diabetic? And that would just be one calculation on that from that binomial formula. There's how you do it. If you wanted the probability of at most 1, so 0 or 1 being diabetic, you just have to do it for 0 and for 1 and add them up. Or alternatively, for at least 1, you could either calculate using x equals 1, 2, 3, 4 and add all those up, or it would be less work to just do the calculation for x equals 0 and then calculate 1 minus that. Because all possible values, probability has to add up to 1. So when you have a large n, if n equals 1,000, in fact, anytime n and n times 1 minus p, so that is the successes, the expected number of successes and the expected number of failures are both, say, larger than 10. You'll hear different rules of thumb. I don't know. Some textbooks say greater than 15, whatever. We're not going to try to trick you by giving you a value of 12 or something. For large sample approximation, those distributions that you saw will be very, very close to a normal distribution with mean n times p. So that's your expected number of successes. Remember, with the one with 20 trials, probability of 0.5, the peak was at 10, so that is the mean. And the standard deviation given by this, square root of np times 1 minus p, where p is the probability between 0 and 1, not the percentage. And then you can just use the your standard normal, well, you can use your normal distribution. It's not going to be standard normal because the mean and standard deviation are not 0 and 1, but it's a normal distribution, and you can then use that standard normal to do these problems. As a side note, part of the reason it's hard to really give a hard and fast rule about, you know, N10 and 15 is that it depends on what part of the distribution you're looking at. If you're looking kind of close to the middle of the distribution, that starts looking normal real quickly. If you're looking way out in the tails, then it starts looking less normal. Imagine that case of n equals 20, probability of 0.5. Near the center of that, it looks very normal. If you get around near 0, obviously it's not going to be as normal, because in the normal distribution you have non-zero probabilities for negative numbers, and that's not the case for a binomial distribution. You can't have negative values. So just as something to keep in mind, these rules of thumb are just rules of thumb, and we'll have more of them for later for the t-tests and other things. We'll say, you know, n greater than 10, whatever, but it's just a rule of thumb. If you look at these, so plot here, here's that example of n equals 20, probability of 0.5, and the binomial distribution probabilities of each number of successes, with n equals 10 being the most probable. If you calculate the normal distribution using that mean and standard deviation that I gave you and overlay it, it will just overlay nicely on top, like you see here, which is why you can use it instead of the binomial distribution. And you can do the same problem using both and actually see how close they are. So if you were asked, what is the probability of having between 5 and 8 successes inclusively, this is how you would do it with the binomial distribution, just by adding up those 4 probabilities. And here's how you would do it with the normal distribution, by going somewhere in between, like 4.5 and 8.5, and calculating this probability by looking up 2 values in your standard normal distribution table. One more example. I guess we can maybe go through this quickly. So the probability of observing 59 or fewer samples in a sample of 400. So n equals 400, probability equals 0.20, and x equals 59 or fewer. So a sample of 400, we're going to want to use the normal approximation, because 400 factorial is probably going to cause an error in your spreadsheet. So the mean is 400 times 0.2. Standard deviation is the square root of 400 times 0.2 times 1 minus 0.2. And then the value of z, whoa, shoot. Oh man, I lost it. Okay. It's recorded. I post it to the Google group, and we can make sure we get it right. I'll put a solution there. Yeah? So the value of z, I got there the values of mu and sigma. Then z equals 59 minus mu over sigma. And then what we want is, so mu was 80 here, and this is 59, so it's going to be a negative. It's going to be a negative value of z. This is 0, this is z, and we're going to want to calculate that left tail probability, and it's going to be something less than 0.5. It's negative because the observation is less than the mean. So we've observed the number of successes here, or smokers, is 59, and the mean, which is the number of trials 400 times the probability of success, which is 0.2, that's 80. And since our value of little x is less than 80, the z will be negative. All right, in case you forget what normal is, here's a little thing to help you there. guess it's hard to see. This is normal. This is out of control. And that's it. So next, we'll go down to lab.